You might want to ask yourself just how accurate are these meters when this circuit is drawing its DC input power into this circuit that is actually oscillating at 188.9 kilohertz. Okay, well, let's take a look at the waveforms here. These are the waveforms. The top waveform there is the battery voltage. This is measured across the battery, or actually across the DC input to the board. So this is the supply voltage, and then this is the current through this 1 ohm non-inductive shunt resistor right here. Okay, so the voltage is being displayed at 20 volts per division with a 10x probe, and the current is being displayed at no attenuation at 1 volt per division, and that translates to 1 amp per division. Okay, so there's one full cycle of the waveform. Off, current comes on with the pulse and then goes off, and then this is the voltage here. Okay, so you can take this current peak here, and you can see that it comes to about 1.8 is the peak current, 1.8 amps, and then if you kind of square that off, instead of having a hump like that, you could call it a rectangle at a peak of about 1.6 amps, and then that rectangle is about a little bit over a third of the whole period. Call it 0.35 or 0.36 of the whole period. Okay, so let's see what that comes out to in terms of an average current across that period. So if we had, what was it, 1.6 amps times 0.35 duty cycle, comes out to about 560 milliamps, 0.056. And that's exactly what we see, 0.55 on the current. So it's doing a pretty good job of averaging the current. The voltage here, 25.7. So the voltage, we're at 25, and then you can see that the voltage sags a little bit, and then there's this ringing there. So the voltage here really is almost constant across that. If anything, it sags a little bit and then it comes up during the ring. And so the 25.7 there might actually be a little bit of an overestimate of the actual voltage across the supply there. But it's not far off. So we have the current is actually being averaged quite well, according to this little estimate. So I'm going to say that this DC input power reading on these meters is good enough to be useful. It's not wildly inaccurate like you might think. The meters do a really good job of averaging even kind of spiky signals. Now, this is at a particular gate potentiometer setting, kind of the maximum resistance. If I minimize that resistance, you can see that the waveform changes quite a bit. I kind of lost the trigger here. Mostly in terms of the amplitudes of these oscillations. I get a little bit more peak current. The current shape changes. Let me get that on a better display there. Okay, and you can see that there's a lot more ringing. But the really neat thing is the amplitude of this spike now. Remember, we're looking at this at 20 volts per division. Let me put it to 50 volts per division. Okay, so you can see that here we have this spike going up to at least 150 volts. And sometimes I see it going up to 200 volts. So that's actually pretty dramatic there. That's with 0 gate resistance. And when we do that, we can see that the actual input power goes down a little bit. So I cranked it way down to here, basically to demonstrate that you can get a good estimate of the current, and that actually tallies with what you see on the meters. Thanks for watching.